Hey everyone, in this video I'm going to walk you through how I built a scalable, multiplayer-ready spaceship audio system using Metasounds. This was all done in a modified version I made of the Airwiggles Asteroids project, a game created for the Implement Tournament event that I organized together with these brilliant folks over at Airwiggles. I'll cover how I planned and designed the different parts of this audio system, including all of these different topics. As you can see, there's a lot to cover, and since I wanted to share some of the project's challenges and solutions more in depth, this video will be a little longer than usual. I've broken it up into segments going over the different parts I'll cover, so you can either skip to the part you're more interested in, or just watch the whole thing to see how it all comes together. With that said, let's start with an audio demo to give you a better understanding of what's included in the project. When the ship is idle, only the Granular synth layer is audible. Tilting left or right will pitch up the synth layer, modulate the volume and pitch of a light wind layer, and apply a 2D pan matching the ship's position relative to the camera. The ship has two speeds, normal and boost. At normal speed, the slow versions of the thruster and texture layers come in. The thruster layer represents the rear burners, while the texture layer adds a sci-fi texture over the synth. When boosting, the thruster and texture layers crossfade over to their fast versions, and back again when boost is released. Also, engine layers get ducked by the boost on and boost off one-shots, to make the transition hit a little harder. Add the laser shot sounds, and that's everything a ship can do. To test interactions in third-person perspective, I built a testing menu that loads different scenarios, including the single enemy scene. In this setup, I control the enemy spaceship at the bottom of the screen, while the audio is heard from the player's perspective on top. As I fly past the player, we'll hear the Doppler effect, along with the engine layers transitioning between their far and close versions. Each layer crosses at a different distance, creating constant shifts in the mix that keep things interesting. Laser projectiles trigger flyby sounds when they enter a set radius around the player, and they also have a Doppler applied to them. Similar to the engine layers, boosting sounds change according to distance. From afar, they're boomy and muffled, and as we come closer, they become more explosive. And lastly, I wanted to prioritize audio in the mix by threat level. So in this double flyby scenario, audio coming from the ally ship flying by will be ducked by the enemy ship. Alright, now that you've seen and heard all the interactions, let's take a look under the hood and see how it all works. For this project, my goal was to showcase how I design an audio system for a spaceship in a multiplayer game. To do that, I followed three key principles. The project had to be scalable and easy to expand or change in functionality if needed, modular so that each part could be developed, maintained, and fixed separately, and replicatable so that sounds for new spaceships could be easily implemented using the base system as a sort of template. These principles guided all my decisions, starting with how I structured my template spaceship's Metasound source. To keep things clean and easier to work with, I separated my spaceship Metasound source into two main sections. The mixing panel, where I set up all of my input and mixing data, and the logic section contained in this spaceship generic patch, which turns these inputs into a functional audio system. The mixing panel lets me adjust everything that has to do with the spaceship, including master levels, volume and pitch controls, triggers, single assets and asset arrays, interface data like the distance between my source and listener, crossfade settings for close and far layer blending, important data sent from the spaceship blueprint like spaceship speed, tilt angle, and ship type, and finally the Granular synth module patch, which I decided to leave outside of the patch handling all the logic to make it easier to adjust and work on. Besides keeping things visually clean, I built it this way so that the Metasound source could easily be turned into a preset for creating new spaceships. This can be done by finding our source in the content browser and creating a Metasound source preset. The preset graph can't be edited, but it works just like the original source and follows any future changes. To implement and mix sounds for a new spaceship, all we have to do is select any variable or asset we want to change. Select Overwrite Inherited Value, and simply adjust the current value, or select a new asset instead of the old one. Do that for everything, save your changes, and congratulations, you just made a new spaceship! Alright, now that the structure is clearer, let's get into the Metasound source's logic section. Similar to the main part of the Metasound source, the logic section is split into two areas. The left side, where I define and initialize all of my engine loops and one-shot sounds, and the right side, where I mix all my sounds together and apply internal ducking when boosting, Doppler simulation for third-person perspective, and dynamic 2D panning for first-person perspective. There is a lot happening here, so I won't cover every calculation and variable. Instead, I'll focus on these parts, which were more interesting and challenging to make. A concept I wanted to follow on with this project was reusing logic and batch processing sounds that have similar properties, and that's what I ended up doing in this case. I created and reused a patch to initialize all engine layers, handling modulating volume and pitch based on ship speed, and crossfading layers by distance and boost state. I also manually set these booleans for each layer. This way, when I'm inside of the patch, I know if the layer I'm processing is close or far, and if it's a slow layer for normal speed or a fast layer for boosted speed, and use this information to make the layer audible only when the conditions are right. In this patch, each block handles a different function. I'll start with the calculation I'm doing in the bottom section. Properly modulating volume and pitch relative to speed was a little tricky. Since this game is physics-based and uses forces to manage the ship's speed, the actual speed value tends to fluctuate quite a bit, which makes using the speed value a little more challenging. Even when stopping, it takes a while for the ship to actually reach zero speed. To handle this, I created a custom modifying variable. Instead of a simple linear modulation relative to speed, I remapped the value across different speed ranges. This gives me precise control over the values I'll be getting, whether the ship is barely moving, which I refer to as the dead zone, accelerating, cruising at normal speed, or boosting. With that set, we can look at the rest of the patch's signal flow. This section is part of my effort to differentiate first and third person perspective audio. To reduce the amount of wave files played, I only play the far third person perspective sounds if the spaceship isn't the player, using this check. I determine if the ship's audio will be spatialized or not in the spaceship's blueprint construction script, but making sure that inaudible sounds aren't played is just as important. This is where I apply volume and pitch modulation to the engine layer, using the speed modulation value I calculated earlier. After that, depending on if the spaceship is currently boosting or not, I play and crossfade between my slow and fast layers using the isSlow boolean I manually entered. And lastly, in this section I used the isClose boolean to determine if the layer should be audible when a third-person perspective spaceship is close to the player, or rather when it's far away. Leaving the engine loops initialization patch, let's move on to mixing and modulating the combined layers, starting with the engine layer's ducking. To make the boost feel more impactful, I fed all of the summed engine layers into the stereo compressor patch I made, and used all of my summed boost on and off one-shots as the sidechain signal. This really clears a lot of space in the mix for the boost to punch harder. Next in the chain, all of our summed sounds go through the Doppler patch. This patch is super handy and can be really useful in any project, so I'll be spending a bit more time on it, breaking down my thought process and calculations, starting with a theoretical explanation of the variables I'll try to calculate. To mimic and enhance the Doppler effect, I'll calculate two variables that will drive different effects and properties. Let's start with the classic Doppler effect variable. This variable will control a pitch shifter to simulate the perceived pitch change of a moving source. For this example, let's say that the yellow diamond represents the ship, and the blue circle represents the listener. While moving towards the listener, the variable's value should be +1, causing the pitch shifter to raise the source's pitch. As the spaceship passes the listener and starts moving away, the variable should smoothly transition to -1, lowering the source's pitch. I can scale this variable later by multiplying it to increase the pitch shift range, but keeping it normalized between plus and -1 makes it easier to reuse across different effects and processes. Moving on to the second variable, I want to enhance the Doppler effect by adding distortion at the Pass-bys peak, and have it ramp up and down smoothly relative to the ship's distance. Let's simulate flying our ship towards the listener once again. When the ship crosses the max effect trigger distance at a high enough speed to justify distortion, the variable's value will rise until it peaks at the closest point to the player, reaching its maximum value. Once it gets there, it'll gradually fall back down to 0 as the ship leaves the trigger range. With that in mind, let's get into the Doppler patch itself. Looking at the full patch, we can see the calculations at the bottom, while the audio processing happens at the top. The audio routing segment is pretty simple. All I'm doing here is pitch shifting the audio using my Doppler variable, and driving the stereo waveshaper node's mix level using the peak effect intensity variable. Aside from that, I make sure to bypass the Doppler effect altogether if the spaceship is our player, as I only want to apply the effect to third-person perspective sounds like enemy spaceships. Moving over to the calculations, let's start with the Doppler variable. I wanted this logic to be reusable across different sources and patches, so I built it using only data available through Metasounds interfaces, without relying on extra blueprint inputs like locations or speeds. Aside from variables I use to tune and shape the effect, the only input I'm working with is the attenuation distance interface, which gives me the distance between the source and listener. To get the variable behavior I want, I need to know if the source is moving towards or away from the listener. To determine that, I'll check if my previous distance value is larger or smaller than my current value, resulting in either a positive or negative value. Positive means it's moving towards the listener, and negative means it's moving away from it. To do this, I'm using a special feature available in Metasounds called delayed variables. Since I don't have execution pins like I would in a blueprint graph, I can't dictate what order variables will be saved or calculated at, making it harder for me to store my previous distance values. To get a similar result, I can use the delayed variable feature and get the value of my variable from the last block. That way I can compare the change in distance over a constant period of time. I'm interpolating the result to avoid spikes and sudden changes in my values, and saving the result as my relative speed, which is the most important part of this calculation. The next steps are pretty simple. All I do is divide by a normalizing factor I set manually, clamp the value, and multiply by a pitch shift range multiplier, which I set through the mixing desk, allowing me to adjust this range from outside the patch. That's it for the classic Doppler variable. Let's move on to the peak effect intensity calculation. There are two main things I want to check for this calculation. Is the ship moving fast enough to justify distortion? And is the ship close enough to trigger the effect? The relationship between these two factors will determine the variable's value. Let's calculate each of these factors, starting with the speed. Since all I'm interested in is whether or not the ship is fast enough without any regard to the direction of the speed, I'll take the relative speed variable from earlier and save its absolute value. Then I divide it by the max expected speed to normalize the value, making it easier to work with. And finally, to create a proximity variable, I'll divide the current distance between the source and the listener by my max effect trigger distance, and subtract the result from 1. This calculation will always result in 0 if the current distance is larger than the trigger distance, making sure that the result of this multiplication will be 0 if the spaceship isn't close enough. Once it gets closer, the proximity value will gradually increase and decrease in value, making it so that if the speed of the ship is high enough, the distortion effect will get blended in. And that's it for the Doppler logic. With this patch built, I can easily reuse these calculations, just like I did for the laser Pass-bys. Let's take a closer look at how they work. The laser Pass-by sound constructed in the source has two main layers: a long pad tail that plays throughout the projectile's flight, and the laser ricochet one-shot sound that only triggers when the projectile is close enough to the listener. On top of that, we've got the generic Doppler patch, a mixer for blending the layers, a dynamic tremolo effect, and some attenuation processing. Let's go over the interesting bits. The Doppler patch here is a bit different from the Spaceship's version. Instead of handling all the pitch shifting and processing inside the patch, it simply outputs the Doppler and peak effect intensity variables. This way, I could be more flexible with its use, like using the Doppler variable to manipulate pitch directly through the wave player's pitch settings, or using the peak effect intensity to drive the tremolo depth and frequency dynamically based on distance from the listener. Just for fun, here's a quick demo of the tail layer with and without the tremolo. I also used the peak effect intensity variable to trigger my laser ricocheted one-shots. I could probably get the same result by checking the distance and triggering the sound when the source is close enough to the listener, but triggering it using the same variable that drives all of the effects and attenuation just felt a lot more organic. The Granular Synth engine layer we saw earlier in the Spaceship source was a really cool addition to the project that I want to take a closer look at. The patch works very much like a modular synth. Its output goes through a series of stereo effects patches I made, including a filter, tremolo, flanger, ring mod, and a wave shaper, which all sum up in a master section that handles volume and distance attenuation. Similar to the way I did it in the engine initialization patch, I used the patches on the top row to remap the ship's speed into values that dynamically drive the different effects, but I don't want to go too deep into the chain in these calculations. Instead, I want to focus on the Granular Synth itself and why it's useful for a system like this. This Granular Synth module isn't a native Unreal Engine node. It's a custom plugin currently in development by Maxim Kokoyev and Wouter Meyer, and I've had an amazing time using it in this project. It has all the controls you'd expect to have in a Granular Synth, and like any synth or component, you can create inputs to control and modulate it during gameplay. Since I'm building a scalable audio system that could potentially be the base for dozens of different ships, I wanted to incorporate synthesis in a way that's versatile and let sound designers get a completely new engine sound with minimal effort. Using the Super Oscillator module to achieve that result is possible, but it's nowhere as easy as simply swapping a wave asset to get a whole new sound palette that keeps the same behavior and modulation as the previous engine sound. To give you a little taste of how that might sound, here's the synth layer I'm currently using in the project. And here are a few other examples for the exact same engine settings, but with a different wave asset as the base for granular synthesis. I hope that more people try out this plugin, because I think that it can really be useful in lots of different scenarios. The last part I want to cover is audio prioritization by threat level. The setup is pretty simple. Inside my spaceship's blueprint, I assign each type of ship to a different submix. On the ally submix, I added a compressor and set the enemy ship's submix as the external input. That way, whenever enemy sounds cross a certain threshold, they duck the ally ship sounds. Honestly, this is a pretty rough solution that worked for this small demo. If I had to redo it, I'd probably handle ducking with an audio bus and send information to it using the audio bus writer node. That way, I could be a lot more deliberate about which sounds are dangerous and should probably have more weight when ducking. And that's pretty much everything in this project. I hope that this deep dive into my technical setup and thought process was interesting to watch. If you're looking for an Unreal Engine project to use as a learning tool or audio playground, the Airwiggles Asteroids game just might be the one for you. It's completely free and it comes with a lot of resources that'll help you get started with audio implementation in it in no time. Check out the link below if you want to learn more about it. Thanks for watching, and I hope you have a great day.